So the next talk here is Mosaic Pages by Jaehyun Han. He is a PhD student at UNC Chapel Hill, and he's one of my collaborators on this paper. So go ahead, Jaehyun.
Yeah, thank you for the introduction, Jayneel. Hi, I'm Jaehyun. Today I talk about mosaic pages, big TLB with the small pages. This graph shows the RAM capacity versus TLB reach over time. The blue line shows the rises to RAM reported on spec CPU benchmark, and this red line on the bottom shows the TLB reach of Intel CPUs at the time. As you can see, the gap is growing. In the latest Intel CPU, TLBs can reach about 8.6 megabytes with 4 kilobyte pages, which is 0.002% of RAM. The gap between RAM capacity and TLB reach is growing, and the gap hurts the performance of application. Many solutions available to increase the TLB reach. The problem is that most solutions depend on physical contiguity. The challenge of physical contiguity is memory quickly fragments. This is because we allocate objects of different sizes. For example, recent work reports the performance of transparent huge page in Linux. In non-fragmented system, the performance increases by 29%, but in 50% fragmented system, performance decreases. This is because of the defragmentation. Physical contiguity can be expensive. In this work, we present mosaic pages. Mosaic pages increase TLB reach without physical contiguity. Therefore, mosaic pages do not have defragmentation cost. We present end-to-end system co-design and implementation, from architecture to the OS, with strong theoretical guarantee. In our evaluation, mosaic pages reduce TLB misses up to 98%. In addition, mosaic pages are compatible with other TLB optimizations. These are the contributions of mosaic pages. How do we do this? We store multiple translations in a single TLB entry. In this figure, we store 4 translations in a TLB entry. These 4 PFNs are not necessarily physically contiguous. Still, these 4 PFNs are virtually contiguous, which allows us to exploit the virtual locality. Now, with 4 PFNs, even though VPNs are 2 bits shorter, the TLB entry is wider. So, we compress the PFNs. We call this set of compressed PFNs mosaic page. We are leveraging virtual locality. However, mosaic pages do not require physical contiguity. Then, how to compress the PFN? We compress the PFN by reducing associativity. Fewer choices means fewer bits. Mosaic reduces associativity of page mapping, which means a virtual page can be mapped to only a subset of physical page frame. In our prototype, we have 104 choices, which can be expressed in 7 bits. This is in contrast to the conventional virtual memory schemes, which are fully associative. When all of these 104 choices of page frames are already in use, we resolve this associative conflict by swapping. The major contribution of this work is we reduce associativity of page mapping without increasing the associativity conflicts. We organize system memory as a hash table. For page mapping problem, we need these 3 properties in a hashing scheme. Low hashing associativity for each item. The set of possible positions in a hash table is limited. Low associativity conflicts, the hash table does not force to evict hot paging. And stability, if we insert an item, the item will not move until deleted. Until recently, no hashing scheme provides all of these 3 properties. Recent publication, iceberg hashing, supports all three properties. You may notice the majority of authors in this work is overlapped with our work. This is because we designed this hashing scheme specifically to solve this page mapping problem. With low hashing associativity, we can compress a PFN into 7 bits. With low associative conflicts, there's absolutely no swapping before 98% of memory is used. And even after, Mosaic has comparable swapping to Linux. And with stability, there's no maintenance cost. So we organize system memory as a hash table with these three properties. Now let's see how page mapping happens in action. This array represents a physical memory organized as hash table. Each row represents a hashing bucket, and each row represents a 4 kilobyte page. We input virtual page number into iceberg hashing, and the hashing scheme returns 7 buckets with overall 104 choices. Again, this can be expressed in 7 bits. OS allocates an empty slot, and CPFN encodes which of 7 buckets the page located, and the offset of the slot of the bucket. This is a sketch of Mosaic page mapping, and there's much more details on structure of hashing scheme available in the paper. Now, let's see how to translate an address in Mosaic. Virtual address consists of VPN, Mosaic offset, and page offset. We use VPN to look up a TLB entry. In parallel to the TLB lookup, we input VPN into iceberg hashing. At the same time, we use Mosaic offset to find corresponding CPFN, which says bucket 5, offset 3. Iceberg hashing returns 7 buckets, and we can find the target page frame. In evaluation, we are going to answer these 3 questions. How much does Mosaic reduce TLB misses? Does Mosaic increase swapping? Does Mosaic increase TLB latency? To answer these questions, we implement 3 components of a system. First, how much does Mosaic reduce TLB misses? To answer this question, we implement Mosaic TLB in Gen 5 simulator. We run a Gen 5 simulator in full system simulation mode with Mosaic TLB. This graph shows the TLB misses normalized to the TLB misses of vanilla TLB. The number after Mosaic represents the number of translations in a TLB entry. Mosaic 4 means we use the same TLB width as the vanilla TLB. Let's see the Graph 500 example as it shows the strong results. With Mosaic 4, we achieve up to 81% TLB miss reduction. If we want to store more than 4 translations in a TLB entry, we need to widen the TLB entry. With the wider TLB entry, we achieve up to 98% TLB miss reduction. So Mosaic can indeed reduce TLB misses. The second question is, does Mosaic increase swapping? The concern is Mosaic reduces the page mapping choices. So now, associative conflicts cause swapping. To answer this question, we implement Mosaic page allocator in Linux kernel and run it in the bare metal system to see the cost of the swapping. We run a workload with varying size, and we give the workload 4 gigabytes of RAM and 4 gigabytes of swap space. For comparison, we run the workload in vanilla Linux with C groups. This graph shows the number of swap operations for each size of workloads. As you can see, both Mosaic and vanilla Linux have similar level of swapping. The final question is, does Mosaic increase TLB latency? To answer this question, we implement hash functions in Verilog and physically synthesize the code and perform the timing analysis. Iceberg hashing evaluates 7 hash function results concurrently. We think this is feasible, and so for confirm, we implement this and do the timing analysis. So we implement the concurrent hash functions in Verilog. And when we synthesize this in FPGA, the evaluation takes a clock period. And then we synthesize this into commercial CMOS process, which runs at 4 gigahertz, and the evaluation takes less than a clock period. This shows the hash function won't lengthen the cycles. In summary, Mosaic increases TLB reach and reduces TLB misses. We achieve up to 81% reduction in TLB misses with the same TLB width as the vanilla TLB. And we achieved up to 98% reduction in TLB misses with the wider TLB entries. Mosaic doesn't increase costs. We showed that we have comparable swapping to vanilla Linux, and there's no defragmentation cost. And Mosaic doesn't increase the latency. Furthermore, Mosaic is comparable to other TLB optimizations. We are not proposing to use Mosaic instead of huge pages. If you want to use huge pages, you can use huge pages in Mosaic. We present Mosaic pages, which increases TLB reach without defragmentation. Thank you for your attention, and I'll take any questions.